So, series and parallel circuits. We've gotten to the point where we've talked about resistance and voltage and current. We've talked about the parts of a circuit. And now we're going to talk about two basic different types of circuits. These are simple circuits. In the real world, circuits are combinations of these. So this is a very simplified version, but it'll give you a good idea of what's going on. And so you need to know a little bit of vocabulary for this. One of them is the equivalent resistance. And you'll see equivalent resistance or total resistance depending on the book or the source of information that you have. On your equation sheet, they call it equivalent resistance, and it's just an R. So it's just a capital R on the equation sheet. I tend to use RT just simply because you're going to have multiple resistors in a circuit, so you'll have R1, R2, R3, and so on, and it just helps keep it straight. The next one is a voltage drop, and that's the amount of voltage that changes when you have a current pass through a resistor. So if we have a really nice simple circuit here, put some resistors on here, we have our voltage source, and so make it an easy thing. This will be a 6-volt battery, and our current's going to come around to this first resistor. And so we're going to have some voltage drop here. And then the current's going to keep going around, and we're going to drop some more voltage. And then we're going to come around to here, and actually we end up dropping the rest. So by the time you get back to the battery, you have 0 volts left. And so if this was a circuit with equal resistors, you'd drop, well, I don't know, 2 volts here, 2 volts here, and 2 volts there. That adds up to 6 volts, and you get back and your battery pumps more voltage in. Alright, so the first type of simple circuit is a series circuit. And this is a circuit that has one loop for current to flow. So in this case, the current starts here, and it only has one path to choose from to get back to the battery. No other branches to break off at, just one big loop. And this is important. The total resistance is the sum of all the resistors. And I'll show you the equation for that in a second. And just like we talked about previously, the total voltage is the sum of all the voltage drops. And so, hiding behind this box is the equation. This is the equation for the total resistance for the circuit sitting next to it. If you have a whole bunch of resistors, you just keep adding them on. And it just keeps going. So you just add up all the resistors you have in your series circuit. So you guys did the bulb activity, you've played with some of the circuits. So if the bulb was burned out, or you didn't connect up the battery, or somebody wasn't holding the wire up on the battery right, what happened? So if you think about it, you couldn't light up the light bulb. And that's because if there's a break anywhere in the circuit, no current flows. The light bulb won't light, whatever it is you're trying to run won't run. There's nowhere for the current to go. The current gets here, and it stops. Wow, I have to keep moving this thing around. Sorry, guys. Okay, so we have a mathematical example. I know you guys love this part, working with the math. First thing you want to do is draw your circuit diagram and label it. So, and it is part of the given. So we have our battery. In this case, the battery is actually a 12-volt power supply. 12 volts. So there's our voltage source. We have a 2 ohm resistor and a 4 ohm resistor. So there's one resistor, there's our other resistor, and it goes back. So R1 is 2 ohms, R2 is 4 ohms. And our voltage is 12 volts. So that's good enough for given right there. Don't have to redo the list. So I'm going to find the equivalent or total resistance, and the total resistance is just the sum of the two resistors. And it is that simple. 2 ohms plus 4 ohms. And so our total resistance is 6 ohms. And I get that you're not going to want to write the workout. I know that, but I do want to see the equation. That way I know you know what you're doing. It would be great to write out all the work, but on something that simple I would understand it. Now we have to find the current. So we go back to Ohm's law. I is V over R. Our power supply is a 12 volt power supply. Our total resistance is 6 ohms. And so our current in this circuit is 2 amps. So that's really nice and straightforward. And so we've already done this. We drew our circuit. And what we want to do is find the current in the 2 ohm resistor. So I guess I will redraw it just to be. So there's our 2 ohm and there's our 4 ohm. 12 volts. R1 is 2 ohms. R2 is 4 ohms. Mostly for me. Maybe it'll help you. So there's my resistors, my power supply. And what I'm going to find is just the voltage drop here. The voltage drop in resistor 1. The current in the 2 ohm resistor is going to be the same everywhere. So we found our current to be 2 amps. So our current is the same throughout the circuit. The current is 2 amps. And so now all we need to do, we have our current and we have our resistance. So now we can find the voltage drop across the 2 ohm resistor. Ohm's law again. Terrible. So we find out that 4 volts dropped here. And if you know that the power supply is 12, you can now figure out that the voltage drop here is 8 volts because these two have to add up to 12. So remember, if you're getting lost, ask questions when you get to class. We're going to practice with this. You're going to do labs. You will get a lot of practice on this. So now you can fill out the parallel circuit side of your table there. I know it's hopefully not too out of order for you. But parallel circuit has multiple loops. And the idea is if the current comes out of the supply over here, gets to this point, it can go this way or that way. So it's got choices to make. And the total resistance is going to be a little bit more complicated to find. Total resistance is going to decrease with every resistor that you add in parallel. And so you have this equation right here, which is 1 over the total resistance is equal to 1 over the resistor 1 plus 1 over resistor 2. And just like before, if you have a whole bunch of resistors, you just keep adding them on as the denominator of fractions. And if you think back to the light unit, we've seen equations like this before, and you do have to work with them very, very carefully. So as you add resistors, the resistance decreases, the total resistance decreases, which is kind of cool. And so if you break one of these resistors, the current still has a path to flow. It can't go this way, but it can continue on here, go back around, and go there. So if you imagine your neighborhood's actually wired in a very complex fashion, but it is parallel. So if somebody drives into the transformer behind your house, my house still stays lit. Neighborhoods are wired this way, houses are wired this way. If you blow a fuse in your house by hair dryers and curlers and all this other stuff going on, your refrigerator still works and the lights are still on in other parts. That's because you only break one part of the circuit, not the whole thing. Alright, so now we have our parallel circuit example, and it's set up a lot like the last one, only the big difference is going to be that we have two resistors in parallel. I have the same values, so you can kind of see what happens to the numbers. And so we have a 12-volt power supply. Our first resistor is 2 ohms, and our second resistor is 4 ohms. There's my given. And so to find the equivalent resistance, we have to be careful. We have to find common denominators or use the inverse key on the calculator, and then use the inverse key again when you're done. So this is going to be 1 over 2 ohms plus 1 over 4 ohms. That's equal to 3 over 4 ohms. And remember, this is the answer to what is 1 over RT. So to find what RT is, you have to flip both of them. So RT is equal to 4 ohms divided by 3, which is about 1.3 ohms. And so now we can find the current. We know the voltage is 12 volts. We found our resistance, back to Ohm's law, V equals IR. And when you rearrange it, you get I is V over R. So that's 12 volts divided by 1.3 ohms. And that is going to give you about 9 amps. I'm rounding, but it's about 9 amps. You probably got 9.2 if you're doing this along with me. And so now we know the current in the entire circuit. We know the resistance of the whole circuit and the voltage of the whole circuit. So now it's time to look at just a piece of the circuit. And so we're going to have our circuit drawing again. There's our 2 ohm resistor. There's our 4 ohm resistor. And our 12 volt power supply. And so the equivalent resistance we found 1.3 ohms. And the current in the circuit is 9 amps. We know both of those from the previous problem. The voltage in a parallel circuit is the same everywhere. So we actually know the voltage. It's 12 volts. Voltage here is 12 volts. Voltage here is 12 volts. And so to find the current in the 12 ohm resistor, in the 2 ohm resistor, I is V over R. So this is our resistor. Voltage is 12 volts. So our current is 6 amps. And so that's how you find the piece in the first resistor. Now if you know this one is 6 amps, and we know that this is 9 amps, then just like the series circuit added voltage, the parallel circuit adds currents. Alright, so this is kind of a summary real quick. You can kind of flip through this, make sure you got your whole table filled out. You might have some extra, you might need to add some, but this will give you a pretty good comparison of the two different types of circuits. We'll get to work with these, we'll get practice with these, there's no reason to worry. Should be interesting and fun. Math is not too bad if you remember to flip that parallel resistance equation. So you guys have a great evening. Bye-bye.